Okay, physics fans, what does this image have in common with this image? Have in common with wow. Oops. Yeah, what do they all have in common? Well, make a guess. Here we go. Welcome back, physics fans. So what was your guess? Was your guess momentum? That's what we're starting now. Momentum in one dimension. So here we go. There's a handout there on the web there, on the Moodle, in case I didn't hand it out to you already, which of course I couldn't have because you weren't there. So, we're doing momentum in 1D and impulse, which is chapter 3.2 in the workbooklet. If you're still following along, please do. If you notice in the workbooklet, there's only 3 pages in there. 3 pages to make up chapter 3.2. Then there's questions, but the 3 pages of notes. 3.1 was forces. 3.3 will be momentum in 2 dimensions. 3.4 is energy, and 3.5 is conservation of energy. All there, just so you know what we're doing and where we are. So this is going to be a short lesson. Maybe it won't be, depending on how much momentum I have here. Newton's second law can be rearranged in this. So we have Newton's second law, F equals ma, and a is the change in velocity over time. Okay, and the change in velocity is final minus initial, but I've also moved the time over to here, move it over, so that we get the force times the time is equal to mvf minus mvi. Mass times velocity is an important quantity. This quantity here, mass times velocity, is an important quantity. We call this momentum. Okay, and we give it a letter, little p. So our formula could be this one, or this one, or it could be this one. Okay, so momentum initial, momentum final is mvf and mvi. And if you want, once we're done, come back to the very beginning. Here are 2 minutes, and I'll try to put this up again. That these are the things that you have to do from the checklist. The checklist for momentum at the beginning of the chapter, the beginning of chapter 3 has this little checklist. And these are the practice problems you have to do from there. And they will only take you maybe a minute, if that, for each one of them. They shouldn't go very long. It should be very little. Okay? Okay, one thing to note, momentum is a vector. Okay, why is momentum a vector? Because velocity here is a vector. So let's move on and let's try some questions right away. P equals mv. It's still working with Newton's second law, but we're just going to look at it a little bit different. P equals mv. What is the momentum of a 10,000 kilogram railroad car moving at 1 millimeter a second each? So P is equal to mv. M is 10,000 kg times 0.001 meters a second, and this is going to be east. So the product of that is 10,000 times 0.0. This will be 10 kilograms meters per second, and it'll still have the direction east. What is the velocity of a 0.05 kilogram baseball moving with 2 kilogram meter per second north of momentum? Okay, we're given the momentum and the mass. So this is just, again, easy math. Let's just go on here. P equals mv. Just get a couple practices using this simple formula. So P is 2, and M is 0.5, 0.05. Okay, and I'm going to just erase this too. I'm not going to go to easy right now. Let's just go extensive here. Let's go in verbose mode. Put the units down and the direction, and that'll be north. Okay, there we go. There's an equal. So the math is just going to be V is going to equal 2 over 0.05. Okay, let's pull up the calculator, clear it here. 2 divided by 0.05, and that's going to be 40. Now, this was kilograms meters per second, and this is kilograms. So the meters per second north will still be up here. So the units will still be meters per second north. It makes sense. What is the mass of a car moving at 20 meters per second south if its momentum is that? Try it ahead. See if you can get my answer. Here we go. I just paused it for a few seconds to get ahead. M is P over V, just rearranging it. Mass is momentum, which is 30,000 kilograms meter per second south, all over V, 20 meters per second south. The south cancel, the meters per second cancel, and we get 30,000 divided by 20. 30,000 divided by 20 is 1,500. Okay. Momentum means the amount of motion an object has. How is this different than inertia? The amount of motion. This is from Sir Isaac Newton, the amount of motion. Okay, he knew this was different than inertia. Inertia only has to do with mass. An object is mass times velocity. So if the object is stopped, it'll have zero momentum, but it'll still have inertia. And change in momentum is just that. Momentum final minus momentum initial. Remember your directions, please. So the change in momentum is just mvf minus mvi. And we go that way because that's where the formula is headed, right? We have the mvf minus mvi is, so we're headed down to a little bit more detail here, understanding momentum. So mvf minus mvi, slowing from 15 to 10. Okay, so the change in momentum is mvf minus mvi. We have to remember direction. Always remember our directions now. This is a vector. So 2,000 times final will be 10 meters per second east minus 2,000, and it was going at 15 meters per second east. So this is 20,000 kilograms meters per second east, and this is 30,000 kilograms meters per second east. So that becomes negative 10,000 kilograms meters per second east So the answer will be 10,000 kilograms meters per second west. Okay, that's the change in momentum is towards the west. A baseball, which is 145 grams, is being hit by a swinging baseball bat. The fastest recorded pitch that I Googled was measured to be 48.5 meters per second, and the fastest recorded batted ball was 54.4 meters per second off the bat. What would be the change in momentum of the baseball? So the baseball is headed this way to begin with, and then after the bat, it's headed that way. It's smacked back. Just think one-dimensional right now. So the change in momentum is mvf minus mvi. So pause it, work ahead, then catch up to me. So you have 3 seconds to pause it. 1, just click on the screen. 2, click on the screen. 3, pause it. Did you get this so far? Did you pause it yet and just took a sneak peek to take a look? I just put my pitcher to the left there and my batter to the right. So the ball was being from the pitcher. The batter hit it back. So I used left and right here, but I'll come back to this picture afterwards to get the directions. And I plugged in the numbers. Okay, pause it and see if you can get the answer. And then unpause it to see mine. Well, there you go. So it has 7.888 to the left, final, and when it was going in, it went in at 7.0325 to the right. We have to subtract them because that's what the difference in change in is, but it's a negative and it's a different direction, so we make it positive and we change that to left. We add them and it becomes 14.9205 kilograms meters per second left. That's the change in momentum of that baseball. Any questions? I don't see any hands, so let's go on. Here's the next page. This is copied from the workbooklet. An unbalanced net force acting on a body changes its motion so that the rate of change of momentum is equal to the unbalanced force. Okay, so just rearranging it back. We did originally move the T over here. Now we're going to move the T back underneath the change in momentum. So the rate of change of momentum with respect to time, how fast momentum is, equal to the unbalanced force. What is impulse? Impulse, continuing on, impulse is the product of force times time and is measured in Newton meters. Newton times meters, and it is a vector as well. Therefore, an impulse results in is equal to a change in momentum. So force times time is equal to the change in momentum. So impulse is force times time, which is the change in momentum, which is mv minus vf, which is the change in momentum. So the change in momentum is equal to the impulse. It's the same thing. So a Newton second is equal to a kilogram meter per second in units. This is the impulse one, and this is momentum. And not just momentum, the change in momentum. Okay, so this brings in force and time into the calculations. Let's just understand a little bit about impulse. So 2 eggs are dropped from the same height. One hits the floor and breaks, and the second hits the water and survives. It splashes down. Why does the second egg survive? Okay, or you have a building and one person jumps from the building, well, that'd be pretty tough, and bends his knees when he lands on the ground, and the next person jumps from the building, oh, I can't even think about it, and doesn't bend his knees. Bam. Oh, ooh. Oh. Okay? The force happened so quickly that it broke the egg. Here, the force was kind of over time. It took time to apply that force to stop the egg. Here, bending the knees takes time. And as you bend the knees, it takes time. This one, I don't even want to draw that. That's owie. Why are bungee cords made of rubber and not steel? Because this spreads the force over time. So you get a bigger time, and force times time is the impulse. Here, if you hit steel, it's going to take a small amount of time, but you're going to get a large force. And large forces we don't like. We definitely don't like large forces. Okay, let's just do question number 6A, 6B, and 7, and we'll call it a quits for this video. 6A says in 5, where the change in momentum was 14.9205 is the final. So the change in momentum was 14.9205 kilograms meters per second, and the direction really is towards the pitcher. Whereas I drew to the left. So what is the impulse now? Well, the impulse is the same thing. The impulse is 14.9205 and Newton seconds, and it's still towards the pitcher. Now, you could mix up these units and it would still be correct since they are equivalent, just kind of like the force of gravity is mg, and we write down kilograms meters per second squared, or we could write down newtons. Just the same, we take one s up there, and now we have Newton seconds is kilograms meters per second. Oh my goodness, we were playing with it so close. So if the ball was in contact with the bat for 0.7 milliseconds, then what was the force the bat hit the ball with? Oh, okay, so the impulse is the force times the time. So the force is equal to the impulse all over the time, and the impulse is 14.9025 Newton seconds, and the time is 0.0007 seconds. So let's pull up our calculator, and we take that number and divide it by 0.0007, and we get an amazing number here of 21,315 newtons. And we still need a direction, and so it'll still be, this was still towards the left if you want. Or again, the left from the picture above was towards the batter. Towards the pitcher, sorry. And that's an amazing amount of force that the ball hits with. But of course, we're talking about fastest ball changes at all here, hitting the base, the fastest pitch and the fastest that's been recorded. But 21,000 newtons, kaboom. That's a big force. Massive acceleration. Because force is equal to mass times acceleration. This is the force divided by the mass of the ball, which was 0.145. And we got an acceleration of 147,000 meters per second squared. Divide that by 9.8, and the baseball would experience 15,000 g-forces. Wow. What is the stopping force on the car in question 4 if it took 20 seconds to slow down from 15 meters per second to 10 meters per second? Last question. 15 meters per second to 10 meters per second. So in question 4, it was the car, 2,000 kilograms doing this, and its change in momentum was 10,000 kilograms meters per second west. So the change in momentum was 10,000 kilograms meters per second west. Okay, and that's going to equal force times time. And we're force times time. And by the way, that's the net force, in case you didn't know it. And it took 20 seconds, so you put 20 here and solve for force. So force is going to be this 10,000. 10,000 divided by the 20 seconds. And it was a force of only 500 newtons. Now, careful, that was to the west. The car's heading east, but slowing down. There's a force slowing it down to the west, and that's it. Thank you very much, physics fans, for following through this lengthy video. Let's start part 2 in a second. Okay, take a bit of a break.